Right. Now let's move on to the next topic, which is the UML based use cases. Right. Now, earlier we looked at various documentation techniques, right? And we looked at the structured analysis. Right. Now, none of these none of the the projects or the programming is done using structured way or the procedure oriented programming. Right? People have moved on from the structured analysis to object oriented analysis. So let's get some context about what is object oriented analysis and why UML is used for that, and what is use case. Use case is one of the UML diagrams. So let's get that understanding about what exactly is the link between these object orientation, UML, and then the use case, and then we'll then look at how do we document requirements using use cases, right? So this session will give you a context of why we have started using use cases and moved on from the data flow diagrams. Okay. Now, primarily, if you look at the programming languages, almost all the programming languages these days are object oriented. Okay. So earlier, most of the programming languages were process oriented, which means there used to be a process. Right? So you have to have a step-by-step process that you're doing, and then maybe you'll have a process, and then you try to automate it. They translate it into a system, and then you are working with the system for automating this process, right? So all you did was you document a process and then automate it, right? So that is where your data flow diagrams are very much useful to depict that process. Okay. Now the main problem with this was, if let's say in this process, if one step changes, it's difficult to identify what is the impact of that change, right? So it's all like one large complex system, and one small change you'll have to retest the whole system, right? So it became difficult to maintain those systems, right? And as and when the earlier days, the use of systems was mostly to automate something. You had a manual process. Earlier, everything was done manually in the 70s and early 80s, right? At those time, the intention or objective was just to automate stuff, right? So if you can use a computer to run the payroll, or maybe update the interest, so that was a very much of efficiency that they have gained. So they just focused on that particular process and then automated it. But as and when the processes become complex, it became difficult to maintain those systems, right? So a lot of those systems became unwieldy because the complexity increased. All right. Now, so people started looking out for different ways. Can we move away from that process-based approach and then look at a different way of programming? Which is much more easier to maintain, right? So that is where object orientation gave a different perspective. Okay, object orientation primarily involves the way you look at your real world, right? It simulates the real world. So what happens in the real world? There are multiple objects. Right, so everything can be considered as an object, right? So there is a customer, there is an employee, then there is a order which is placed, there is a product which is available, right? So in real life there are multiple objects, and then there are interactions between these guys, right? A customer would talk to the employee to get something done. A customer would place a product, right? And then he would pay the bill. The employee would generate the invoice, right? So if you look at the real world, it's nothing but a bunch of objects interacting with one another, and each interaction is independent, right? So if this interaction changes, there is no impact on the on maybe in these interactions, right? So what people thought is, let's simulate the real world in a system, right? So they went for this approach where they identified the objects, they defined what an object is, and then made them interact to actually perform the same task of what we are doing in real world. Okay, so that's exactly is the underlying concept of object orientation. So the main two advantages which came out of it was modularity and abstraction. Okay, now what modularity means is, if I have to put it in simple terms, right? So a large complex system, right? Now it's difficult to understand for one person everything end to end, right? But if I have, say, instead of one large big system, if I have smaller systems, right? And each one of them is independent of another one, right? So I can have 5 people work on each one module, and they understand that module in and out, so it's easier to maintain, right? So the complexity is reduced. So since if I change this, the impact on this is very minimal, right? So these two can coexist, right? So there can be 5 people looking at each module each, and then manage a large complex system by breaking it into modules, right? Similarly, the other part is, the modules or objects should be able to interact with one another, right? And then use some functionality, right? Now, both these concepts can be easily explained by taking an example of a car, right? So let's say you have a car, okay? Now, let's say you have a problem with your air conditioner. You take it to the mechanic and he would fix it. So are you going to test each and every part of your car, like your suspension, your engine, your gearbox? Are you going to test all of that? Not really. You just test the air conditioning because that was the only thing which was modified, or that was repaired, right? So why? Because you're pretty much sure that if I modify only the air conditioning, the rest of them are not even impacted, right? Why would the engine not work properly if the air conditioning is repaired, right? Why? Because there are all modular parts, right? Engine is completely independent of the air conditioning, right? So that is nothing but modularity. So engine is a different module, air conditioning is a different module, gearbox is a different module, right? So a car, if you consider that as a system, it can be broken down into smaller modules, and each module can handle one specific functionality or feature. Okay. The second concept is abstraction. Now, however modular this car might be, these modules might still need to interact with one another, right? Or for that matter, you also have to interact with the car, right? Now, how would you make the car move faster? Okay. Now, all I need to know is that if I press that accelerator pad, the car moves faster. But is that all? What is happening inside the engine? I don't really need to know, right? Why do I need to know what is happening in the engine? Only the engine needs to know what it needs to do, or the mechanic who is repairing that engine needs to know. All I need to know is how to use it, right? So what we are doing, we are providing abstraction to the functionality, right? So to use a functionality, we don't need to know how it is working internally, right? So all I will do is I'll press on the accelerator pad and the car moves faster. Okay. So there is an interface to that functionality, right? So there is a there is a clear button which is given. I press that button or press that pad, and if I press that pad, I get some functionality delivered, right? So this pad or that button are nothing but your interface, right? So they are hiding that the internal logic of how the engine works through these interfaces. Okay, so effectively what object orientation did was it broke down a large system to smaller modules and allowed them to interact with one another through these interfaces, well-defined interfaces, right? So that basically is the main reason why object orientation is so popular. Okay. Now you can forget everything. This is just for your context. Nobody is going to ask any questions on this or anything, right? It's just that the more we know, our job becomes easier, right? So I thought some related topic about why some kind of programming language preferred over another one, right? If you understand this, because your analysis and then documentation techniques would also be aligned to this object orientation. So it makes you do your job better. But again, you won't lose anything if you don't know anything about this, right? So this is more like an additional thing that we have discussed. I've just introduced you to what object orientation is about and what are their advantages over the earlier programming languages. So why was Pascal and Fortran discarded, and then why is Java and .NET widely used? These are the main reasons. Okay. Now again, like I said in the previous screen, I told you that there are objects and they are interacting with one another to perform some process. So how do you define an object? So we define an object by two main things: state and behavior. State is nothing but everything has some data about it, some specific properties. Like if you pick up a car, right? A car would, what is the color of the car? Okay, what is the engine capacity, right? What is the model, right? And various other features that you want to capture about the car. All that would become the data, of the properties, of the state of that particular object. And behavior basically tells what can the object do. What can the car do? The car can move forward, it can move backward, right? It can turn left, it can turn right, right? It can stop, it can accelerate. So these are some of the things which a car can do, right? So together with the state and behavior, we can actually model any real life object into a software. Right? So we'll capture all the data, and then we'll clearly define what all it can do. So it's basically defined in your system, right? So that's exactly how we do it. Now these objects need not be the physical objects. Something like a bank account, right? It's intangible, but it still qualifies for the object, right? So a bank account would have information like account number, what is the amount that is stored in the account, right? It would have details about what type of account it is, what is the interest rate on that. So a lot of details that you will maintain. All right. Then you also can do some activities on the account. You can deposit money into the account. You can withdraw money from the account. You can open an account, and you can close an account as well, right? So that is how an object is defined. And the underlying logic of object orientation, like I've explained earlier, you try to model the real world by making the objects interact. Okay, so if I want to develop a banking software, I'll create accounts, I'll get customers, I'll create employees. Now employees can start a new account. The customer can deposit money, and we can withdraw money, right? So these are nothing but there are three objects and they are interacting with one another, right? So that exactly is how object orientation works. Okay.